thickness here. Okay? So those we still have some uncollected assignments. Okay? Now let's move on to examples. Okay? Some also classical example. Okay, now let's look at the question. What question we are asked to solve? Now the open circuit and the short circuit impedance measured at the input terminal of lossless transmission line of length of 1.5 meter. So means just now we mentioned one section of transmission line short circuit, right? Short circuit. The three impedance, right? Another is open circuit with the impedance. Okay? The open is this value, short is this value. Actually, this approach can be used to, this is very useful example. This can be used to find out the characteristic impedance of this transmission line. For instance, currently, we have no idea about the characteristic impedance of this transmission line. Then think about what approach you should use to find out this. You can one section short circuit, right? Certain lanes, another open circuit. Then you measure one impedance, another impedance, then find out the characteristic impedance of this transmission line. Also, you can find out the propagation constant. Okay, right? So, without changing the operating frequency, find the input impedance of short circuit. That is twice the given length. This is simpler. Okay, it's simpler. Once Z0 and the K have been solved, you can use the transmission line equation. Solve this very quickly. Okay, right? You can use. Then how long should be the short circuit line being big in order for it to appear as open circuit at the input terminal? Okay, from short circuit to open circuit, actually this is, later I will show you. Okay, from short circuit to open circuit, okay, what wavelength it should travel? Okay, it should travel. Okay, from given equation, from the previous equation, short circuit input impedance, sorry. This is given quantities, input impedance for open, short, and the length. Actually, for the input impedance for short circuit can be expressed by, can be given by this equation. So previously, for open circuit can be given by this equation, right? Now this value is given, this value is given, this value is given, this is given. So also we understand tangent alpha, put tangent alpha, right, is equal to tangent alpha times put tangent alpha is equal to what value? 1. So then this times this is equal to Z naught square, right? Okay, is Z naught square. So Z naught is equal to square root. So then just set this and this into this equation. Turns out Z naught is 75 ohm, right? Okay, this is not difficult. So in the meantime, just now is multiply the two equations. Now we divide this and this, okay? The short circuit impedance and the open circuit impedance, then Z naught can be cancelled, okay? Then we have the tangent KL square, okay? So then the K is inverse tangent, right? Okay? So turns out you sub this value into this equation. Okay, again, verify by yourself, okay? So then you can obtain K and Z naught. So in the meantime, what is wavelength? Is 2 pi over K, right? Okay, 2 pi over K. So then for the second is twice the length. Twice the length is, again, we use this equation. Now the length initially is this length, now 3 meters. Okay? So KL, then set into this equation. This is very simple equation, right? Again, verify by yourself. Okay? Verify by yourself. I have mentioned more than 10 times, right? Okay? Okay, another question is short circuit, then by what length it will become open circuit, right? Okay, from this equation, this is the short circuit. Then to give you the open circuit means this. Okay, this is short, right? Okay, by what wavelength? Okay, means this distance. Here. Minimum or shortest distance should be, this is short, then this open, right? Okay, from this equation, here should be lambda over 2. Then for open circuit, this KL should be this value. Means impedance is infinity, right? Is infinity. Okay? Short circuit, the input impedance is 0, right? Okay? Open circuit is infinity. So infinity, this should be pi over 2. The period of tangent of a function is pi, n pi, right? So minimum is lambda over 4, right? Shortest. Also just now mentioned by half wavelength, then the input impedance is the same. Input impedance is the same. This first. Then I will ask you another question. Okay? This is open. Okay? Then the input impedance becomes a short. What is the wavelength? Okay? What is the length? What is the length of this distance? Now is low, is open. Okay? And what is the distance? Of this distance, the loop input impedance will be 0 or will become short circuit. will become short circuit. Okay? Also, from our understanding, previous understanding, okay? The input impedance at what distance the input impedance will be the same is lambda over 2, right? Lambda over 2. Okay? So just now we can, okay, if this is lambda over 2, then input impedance is the same, right? Okay? Quarter wave length, this is open. Okay? So also, this is quite different. Microwave is quite different from what you have learned in the low frequency electronics. Low frequency electronics, short is short, right? Okay, open is open. Now, in microwave high frequency, short circuit could become open circuit after a certain wavelength. Now it's quarter wavelength, right? Okay. However, it is the same outer length of half wavelength. Yeah, of course. Another half wavelength also is the same, right? Okay. By another half wavelength, sorry. This another half wavelength. Also, the input impedance still should be 0, right? Open circuit. The period is half wavelength. However, by quarter wavelength, this short will become open. By another quarter wavelength, open will become short, right? Okay? Open will become short. Okay? Quarter wavelength transformer. Just now also we mentioned this is very, very important concept. Quarter wavelength transformer. From this, okay, maybe we go through when the load impedance does not match with this characteristic impedance. For instance, this typically transmission line, for instance, coaxial cable or coaxial cable, right? Measurement, most measurement coaxial cable or measurement those we use 50 ohm transmission line. Then, for instance, the antenna, the impedance is 100 ohm. Then you need design the so-called mesh network. Okay, the quarter wavelength is very important impedance transformer. Okay, means can be used to design the mesh network, right? Between, for instance, 100 ohm and 50 ohm. Okay, then how to design that part by using what we have learned in this module. Okay? Here we just introduce a very simple, very useful impedance transformer. Okay? For transmission line, so here for insert one section of quarter wavelength transformer, then the impedance, for instance, can match to this impedance if RL is not equal to 3 ohm. Right? Okay? So what is the theory behind of this? What is the theory behind of this? Okay? So the theory actually is here, just here. Okay? The theory. So the theory is, this is transmission line equation. Now, this electric length is a propagation times propagating constant times the physical length, right? Beta L, beta L. Beta L, beta is 2 pi over lambda. Now this length is times lambda over 4, right? So electric length then is pi over 2. If we this pi over 2 just now we mentioned this infinite value, this can be this finite, then can be dropped. Then for this, since this drop, okay, we go right, okay. Then the top and the bottom, the j can be cancelled. Then for this equation, for this top and the bottom, we have the same. Then also can be cancelled, right? Okay. So then there is zq squared divided by RL. Then from here, what you can observe? What is zq? Zq is an impedance, characteristic impedance of this section of transmission line. Okay? On this section of transmission line. How to determine the value of this? Then from this transmission line equation, it is equal to square root of the now input impedance. Suppose for impedance matching input impedance, this Zi should be equal to Z0, right? For impedance matching should be equal, right? Okay. Now Zi is Z0, this is RL. So this is given, right? Just now we need to match. For instance, this 100 ohm, this 50 ohm. Then this ZQ is 70.7 ohm, right? For instance, this is 100, this 50 ohm, right? 50. Then you can immediately design the impedance matching. The impedance matching is this length is quarter wave length, right? Quarter wave length. Then the characteristic impedance is 70.7 ohm from this equation. This is very important relation, right? Very important relation. Quarter wave length, right? Okay. Impedance matching is to eliminate the reflected voltage or current on the transmission line. Why we need to do the impedance matching? Okay. Actually, for this part, we gradually move on to the real work problem. Okay. Previously, when you are asked to calculate electric field, magnetic field, you cannot touch those electric field and magnetic field. However, for transmission line part, those problem questions are more practical, right? Okay, so impedance matching also is more practical technique. The reason for why we need to do the impedance matching is maximize power transfer. Also, we have highlighted many times. No matter for plane wave transmission or plane wave transmission in that is unguided, unbounded medium, right? Okay, then transmission line is guided medium. Okay, guided medium. So objective finally is to maximize power transfer, for instance, from the transmitter to antenna, right? Then transmit to the free space. The input impedance remain constant at value Z0, therefore input impedance input. Okay. Based on the no voltage peak on the transmission line. So why we need this? If equal to Z0, then we can achieve the maximum power transfer. Okay, now let's look at the last example. Okay, in this chapter. This is another very classical example. Okay. Now, what is the problem? Is we have the transmission line. Then power equally divided to, for instance, this load is are two antennas, right? Okay? Are two antennas. However, the input impedance for the two antennas are different. One input impedance is 64 volt, another 64 ohm, another is 25 ohm. Now, bear in mind, it's equal power distribution. Okay? Equal power distribution. Another is now we will use the quarter wavelength transformer. Could be you needed to do is to design the match network for this section and this section. Okay? This section and this section to achieve the equal power distribution. Okay, now the operation frequency is 10 megahertz. Okay, now determine the required characteristic impedance and the physical length of quarter wavelength transmission line. Here, assume this is the phase velocity of the waves traveling on this transmission line. This is now is 0.5 C. 0.5 C means epsilon R. Yes, epsilon R1 and epsilon R2 means epsilon R. This is 1, this 2 is both equal to 4, right? Okay? This will affect the physical length and the wavelength, quarter wavelength, right? Finally, you still need to give the physical length, right? Okay? This, okay, find the standing wave ratio on the match line, means along this transmission line, okay? So, after we design this transmission line, actually along this main transmission line, the SWR ratio, what is SWR ratio? Okay, so to match to this main transmission line, the input impedance looking to the right hand side. What is the input impedance looking to the right hand side? To match with this main transmission line, what is the input impedance? Should be equal to characteristic impedance of the transmission line, right? Okay, so the input should be equal to 50 ohm, right? Equal to 0, 50 ohm, okay? Now, to achieve 50 ohm, since it's equal power distribution, so we should have two parallel resistance with equal value. So means each pass, right? Either this or this. The input impedance. Just now the Z in is overall impedance, right? So for each section, the impedance should be 100 ohm, right? Then in parallel, will give us 50 ohm, right? Okay. Now this Z in 1 is equal to 100 ohm. Okay, for this Z in 2, Z in 2 is here actually. Z in 2 is here. Is also equal to 100 ohm. Z in 2 should be here. This part, right? This part. Z in 1 is this part, right? Okay? Then we will use this. Okay? Right? So then it's not difficult, right? Not difficult. Now we have 100 ohm, 100 ohm, this 64. Then what is the characteristic impedance of this section of transmission line? Is square root Z in 1 times RL1, right? RL1 is a characteristic impedance, right? That is square root 100 times 64. What the value? Is characteristic impedance of this is equal to 80, right? Ohm. Then how about this section? This section, sorry. This section should be equal to square root of 100 times 25, right? That is characteristic impedance of this transmission line should be 50 ohm, right? 50 ohm. Should be 50 ohm for this transmission line. Yes, we have. Then you need to determine the physical length. Is quarter wave length. The tricky part is this 0.5C. Just now the student has mentioned the impedance of R should be equal to 4, right? Okay, not difficult, right? Anyway, this is very classical example. Okay, now let's look at it. So here, now, so the input impedance, look into this stub is 100 ohm, right? Similarly, look into this stub, also 100 ohm. Then the two resistors in parallel will give us 50 ohm, right? Put parallel together will give us 50 ohm, right? So only with 50 ohm, then main transmission line, no reflection, right? No reflection. Also just now mentioned, when this is equal to the characteristic impedance, then no reflection. Okay? So then next step, is the characteristic impedance of each section, 80 and 50. Also we mentioned the epsilon r is 4. Now wavelength based on this equation. This is very important, right? Not if you use a free wavelength in free space, then not great. The tricky part is here, right? If you don't use company, then a few marks definitely will be lost. Okay, will be lost. Disappear. Okay, now this here is tricky point. Then turns out wavelength is this value. What the wavelength is this very straightforward, not difficult. Then how about reflection coefficient? Actually, this is quite straightforward. How about the reflection coefficient along the main transmission line? Main transmission line, the SWR. And what is SWR on the main transmission line? SWR on the main transmission line. So SWR, okay, now we can go through this first. reflection coefficient. So for instance, main transmission line, this pass and this pass, right? Okay, RL1, RL2, right? RL2, this D0, this D01, this D02, right? This R0, okay? R0. Now the reflection coefficient along this transmission line is this, right? RL1, right? Okay. Then S standing wave ratio is this value, right? Okay. Means although it is matched, actually in each star is standing wave, since we have incident and the reflected. Similarly for this merchant section, also the SWR is not equal to 1, right? However, for main transmission line, since this impedance, now this impedance overall is equal to 0, right? So the reflection coefficient on the transmission line is equal to 1. Sorry, equal to 0. Reflection coefficient is equal to 0, right? It's much low, right? It's much low. So S is equal to, along the main transmission line, S is equal to, what is SWR? S is SWR. Based on this equation, what is the value? 1. Yes. Actually, along the main transmission line is traveling wave. However, for metric section of this or this is standing wave, right? So our objective is match this main transmission line, right? Okay. So that's all for this chapter, not for today. Okay. Okay. Smith chart. Okay, just now one student mentioned Smith chart. Smith chart, more for reference for this module. Okay. I will, if I have more time, I will cover Smith chart. Okay. So I would like move on to tutorial first. Okay? Go to tutorial first. The tutorial on transmission line. Who has attempted the tutorial questions on transmission line? Anyone has tried tutorial question on transmission line? No one?
Easier than your assignment.
Okay. So just now also I have already mentioned next week, since some students could come late, right? Okay, next week we have the quiz, right? Quiz will start from 7 o'clock also at our classroom. If the style not it, we will take the normal written style, okay, not MCQ, okay? So we will maybe prepare, I have not prepared, sorry. We will prepare maybe 2 or 3 small questions, right? To test your real, right? I need to understand your real understanding, okay? So understand your MCQ, you could work together in a group of 5, 10, right? Okay? So for us, for second part, okay? You understand? 1 hour. Yeah, only 1 hour. Okay? Open book. Okay? Even with open book, if you don't read through, you have no idea where they are. Okay? Right? Now let's read through the question 3. So the previous 2 questions we have already discussed. Okay? Question 3. Consider a coaxial line with dielectric constant. Okay, now with the dielectric constant, this is very important information, right? When you read the question, okay? Material filling the space, this material, between the inner and the outer conductor. The characteristic impedance of the coaxial line is 75 ohm. The length is 38. This is the physical length, right? Physical length. Then operating frequency is 2 gigahertz. Okay? The line is terminated with 300 ohm resistance. Okay? Determine the impedance looking to the line. I think this is very simple. Is this transmission line, right? Okay. Right? It's just this is very simple. So now the key. So we could have this question. We could have this question in our final exam. How will it appear? We could have the similar maybe question, maybe in 10 marks. In final exam, as we mentioned, we have 2 sections, section A and section B, right? Section A, we will have 5 compulsory questions to answer. Each carries 10 marks, right? Okay? So for each small question could be similar as this, right? put it similar to this one. Okay, then for section B, we will have 4 questions. So covering different topics, each will carry 25 marks. For section B, you only need choose 2 from 4. Okay? So basically, the 4 questions cover from electric field, magnetic field, wave, and transmission line. Okay? Now, you need to translate all this information. How translate this to how you can use the transmission line equation, right? How you can use the transmission line equation. How to use transmission line equation? Very important parameter is KL, right? Is an electrical length, right? So that then tangent KL, right, in the equation. KL is an electrical length, okay? Then you can set the tangent KL equation. You can easily calculate this. Then let me look at the solution. Since okay, the information, given information epsilon r 2.90 75 is 75, this 300, right? This physical length is, since first velocity is this equation, right? First velocity. So then from there you can calculate the k, and you can calculate the k is a propagation constant. Propagation constant, just now I mentioned, propagation constant times the physical length is the electrical length. Right? Then submit to this equation again. So again, you need to verify by yourself for this. Okay. Right? This is not difficult. Then what is the second equation? Specify the position of voltage and the current standing wave maximum on the coaxial line. This now determine the voltage and the current maximum on the coaxial line. Okay. You can use this equation for maximum, right? For maximum. Before that, you need to determine this reflection coefficient. Now the reflection coefficient is this value. This reflection coefficient at the load. Turns out theta L is 0. Theta L is 0. Now theta L is this is 0. Okay? Is 0. Okay? Now is the maximum is n number over 2. N number 2. Lambda also you can calculate since k is 2 pi over k, right? It's not difficult. The minimum is another quarter wavelength. Minimum is another quarter wavelength, right? This plus another quarter wavelength. Okay, here is multiple solution. A is from this value, means minimum is at the boundary, right? Means at the load. Here, boundary is at the load location, right? Okay? This is not that difficult. Okay, so for this question, is could appear as a small question. It's 10 marks. Okay? 10 mark question. Then the question 4. Question 4, also a very classical question. This could be a 25-mark question, okay? Just give you the template. Okay, some students always ask the template, right? This is the template question, okay? Then this question, a generator, this is very classical equation, okay? We mentioned it many times, quite a few times. Now, VG source is source impedance, right? Is source VG, right? Is VG, okay? Right? Okay. Length of transmission line, then the load, right? The load 75 ohm. This is 75 ohm. VG is 50 ohm, right? Z naught, this section of transmission line, 50 ohm, Z naught, okay? The length, this is D, okay? Right? Okay? Now, calculate input impedance. Where is the input impedance? On the, input impedance of the line at the generate end. Generate end is here, okay? Generated end, right? This is the load end. This is the load end, right? Okay? This is generated end. Then, this is very not difficult, right? Just by using the transmission line equation, okay? Then compute the current and the voltage, okay? Current and the voltage, we can simplify this and this. This input impedance, this ZG, right? Okay? Then you can calculate current and the voltage. Okay? This is VG, current I is VG divided by ZG plus ZI. It's very straightforward. Then voltage is current times ZI, right? Okay? Then calculate the time average power delivered to the line. This is input impedance. Input power. Input power is equal to 1/2 real part V in I in, right? Conjugate. Yes, you are right. Might have the conjugate. Okay? Then compute the load voltage and the current at the load, and the time average power PG delivered by the generator, the time average power dissipated in load, time average power dissipated in ZG is conversion of power satisfied. Means you calculate the power from this source, right? Absorbed by this, and the power to the load. Power to load is equal to this, right? Power to the load. This for lossless is this is equal to input power. Input power is absorbed by the load, right? Okay. For lossless, definitely the conservation of power is satisfied. Okay? Then let's look at the solution line by line. Okay, this is very classical, just now mentioned, very classical example. then this can be simplified. Can be simplified as this, right? Okay, simplify as this. Then let's look at the solution. The input impedance means looking to here, right? This is very simple calculation, just by using the transmission line equation. This is the electrical length, right? Electrical length is K is 2 pi over lambda. Since this is 0.15 wavelength, right? So that's why it's 2 pi times this value. Okay? Then just solve. Now again verify by yourself by using the calculator. Okay? Then this also you can verify. Just now mentioned. This has been simplified. This, right? This the G, the I, the G, right? Then I. This is I. This is very simple. This is very simple relationship, right? This voltage I cross the I. Okay. So complex challenge is to do this complex number calculation. Anyway, you need to go through this step. Okay? You need more time to go through. So try to spend time. Don't lose marks. Okay? Try not to lose marks in the complex number calculation. Okay? Maybe, as mentioned, those will make those difference. Then input power also is very straightforward, right? Input power. Okay. Again, verify by yourself. Then the general expression is also important, since we have this expression at any location, then at the generator side, actually at the generator is II, right? At II. Then our idea is to derive IL, right? Okay, then II has been calculated, and then the current at the load, then you can obtain this. Okay, then voltage across the load, then it's just times the load impedance, right? Okay, load impedance. Load impedance, right? As mentioned, current. Okay, load impedance, then the power from the generator, right? Power from the generator. The load power, okay? This is the power by the internal or source impedance, right? Turns out this PG should equal to PL plus P internal, right? Okay? Actually, this also is equal to P input. Okay? Here is internal, okay? We have another P INC, incident, okay? This internal by the source impedance, incident minus reflected power is the PL or PI input, right? Okay, sometimes you could be confused. Okay. So power conservation is satisfied. So those more for okay for this. I will not discuss this question for your own practice. Okay, for your own practice. So today I will stop here. So next session, after the quiz, I will continue the Smith chart. Okay. After the 1 hour quiz, we could spend half an hour to go through the Smith chart. Any question? You can ask. Okay, here we still have some collected assignment 1. Our GA has marked. Okay. For assignment 2, if you have not submit, please submit. Today, if you submit late, small penalty, we have to submit. Okay? Yeah, we will have small penalty. Okay? Okay.